Welcome everyone, my name is Jan Pennekamp, I'm with RWTH Aachen University. Today I'm going to talk about private multi-hub accountability for supply chains. So this work is part of the federal funded research cluster in Aachen, where over 35 institutes are participating to create a worldwide lab. Overall, the goal there is to utilize data from production development and usage to improve the domain of production technology. This also includes information sharing along supply chains, and these collaborations are expected to increase the business performance of participating companies significantly. However, the sensitivity of business data contradicts this data sharing. Now, I'm going to present you the scenarios that we're considering within this paper. As you can see, there's a regular supply chain that consists of different production steps. Already established today, there are product flows on the one hand and information flows on the other hand, where direct business partners exchange information with each other. However, an aspect which is lacking today is the information sharing between indirect partners along a supply chain. Two famous applications of such an information sharing would be multi-hub tracking on the one hand, where you follow a product until it's finally assembled into a final product, or the other way around, where you decompose the final product into its individual components. For example, in case of an airplane crash, you might want to identify where a single turbine came from. Now, the goal for this paper is to combine the needed privacy aspects in the industrial setting with multi-hub information sharing capabilities. As I said, our main goal is to enable accountable multi-hub information sharing. Here we have to consider the trade-off of privacy preservation and transparency. The design goals for transparency on the one hand are accountability, so we want to hold individual companies accountable for their actions. We realize this by using signed fingerprints on a blockchain of all interactions. The second goal in this category would be verifiability. So we want to not only avoid manipulations, we also want to detect them and identify dishonest parties. In contrast to these goals of transparency, the goal of privacy preservation mandates that we should protect business secrets. Therefore, we utilize fine granular attribute-based encryption policies and access control. Our two additional design goals deal with security and scalability. So for security, we want to prevent unintended information leakage, and we have to deal with mutually distrustful parties. Therefore, we do not require any real trust in our architecture. And then finally, the goal of scalability deals with the size of real-world supply chains. So we want to be able to handle a realistic number of products with our approach. Coming to the design overview, we have 5 individual entities in our design. Centrally, there are the collaborators who record all their interactions to the information coordinator. I'm now going to present you the individual steps that are required to record a supply chain interaction in our design. First, the access guards hand over attribute-based encryption attributes to the collaborators. Thereby, they enable the encryption with ABE policies. Collaborators then can offload encrypted raw data to a dedicated storage provider and combine a link to this information together with attribute-based encrypted information in a data record, which is submitted to the information coordinator. This data record includes tracking and tracing information for this record. The information coordinator then records these traits and production steps and persists them in a database. For accountability, a fingerprint of the respective data is submitted to the immutable ledger and persisted there. Thereby, all the data records that are stored in the information coordinator can be verified. In case of conflicts, we also consider a detached judge that can be triggered on demand. Now, coming to the evaluation. Here we visualize a fine blanking line, which is a high precision stamping production process with a goal to create identical workpieces. Given that we work in a supply chain scenario, we also consider additional pre-processing steps that are required before the real fine blanking production. We also consider all relevant steps that are needed to operate the machinery. This includes operation material and machine tools. Overall, this leads us to a total of 4,000 production steps for a single fine blank part. While this assumption is a worst case setting, it helps us to underline the scalability of our approach. In a real supply chain today, probably the individual steps of the fine blanking line illustrated on the bottom of the slide are probably handled by a single producer and therefore do not have to be recorded individually. Regardless, even if those individual steps would be separated or handled by different companies, our solution is able to deal with them. Now, taking a look at the corresponding evaluation. As I said, we take a look at the different supply chain, at the different lines of fine blanking line. Overall, we consider 100 individual fine blank parts that are combined into a final product in our setting. In this presentation, I'm going to focus on the processing overhead at the information coordinator. For numbers on the attribute-based encryption and blockchain evaluation, please look into the paper. As I said, we need produce and trade records to record the different interactions of the supply chain. Record updates are required to update the tracking data in the utilized product. So as we can see, we have three different scenarios. One where we have individual encryption keys for each component, one where we reuse keys along a supply chain, and one that serves as a baseline without any encryption. As we can see, most overhead is not at the information coordinator, as in the no encryption scenario, the processing times are quite low. This means that the overall head is at the collaborators and the architecture scales well with a number of suppliers, even when using encryption. The processing time of produce records can vary because the number of used components also influences the number of required tracking updates. Therefore, this number is higher when utilizing 100 individual components and not just a single product. Now, as I said, these record updates are required to update tracking data once a product has been utilized in production. Similar to the recording of information, we also allow for information retrieval which is comparable to the insertion of data into our architecture. Here we can make use of bundling to reduce, to improve the processing times. Now, coming to the applications of tracking and tracing. Just a side note, the performance here really depends on the underlying supply chain model. So in our graph, we have a total of more than 800,000 records that need to be processed for a full trace of the whole supply chain. In contrast, tracking of a product just has to follow its path. Here, in our model, the longest path consists of 35 records. Now, the tracing time is significantly longer as more records have to be processed for a full trace. However, tracking or tracing is only a rare event, for example, in case of production errors or plane crashes. What you can see here is the trade-off between privacy and performance for the tracing. So if we reuse AES keys along the supply chain or do not encrypt the tracing information at all, the performance can be significantly reduced at the cost of revealing potentially sensitive information to the information coordinator. On the other hand, we have the tracking, which is significantly faster as we just have to follow a single flow. However, in this case, using multi-hop processing yields no benefits as significant processing overhead is added. The reason here is that we just have to follow a single path, and thereby multi-processing does not yield any benefits. To conclude this talk, we identified that information sharing and accountability along supply chains is currently missing. However, it's expected that this improves the productivity and reduces costs of participating companies. Unfortunately, the information sharing in these competitive business scenarios threatens the privacy of sensitive data. To deal with these issues, we proposed a novel supply chain architecture that utilizes attribute-based encryption policies for security and privacy preservation. We further include a blockchain to record fingerprints of all supply chain interactions to enable accountability. We also support tracking and tracing of individual components with our architecture. Our evaluation then shows its scalability even in tomorrow's settings where production is potentially distributed across various companies. Furthermore, our architecture supports several use case specific adaptations if they are needed. For example, the encryption can be turned on or off, or encryption keys can also be reused. With this, I would like to conclude my talk and thank you for your attention.